For those of you that don't know me, I'm Sherry Jones, the chair of the Department of Special Education and Communication Disorders. I hope you all had a wonderful fall break. I can't think of a better way to come back from break than to have a research seminar, so I'm very energized this morning to introduce to you our speaker. Dr. James Booth is visiting us today and tomorrow from Northwestern University. He did his undergraduate and graduate training in psychology. His undergraduate work was in Ann Arbor at the University of Michigan, his graduate work at the University of Maryland at College Park, and he did postdoctoral work at Carnegie Mellon University. In 1998, he joined the faculty at Northwestern University, and where he's currently a professor of learning disabilities in the Department of Communication Sciences and Disorders. His research is in the areas of language and reading, cross-language differences, learning, brain plasticity, executive function, and mathematics. And central to all of these areas is brain development and plasticity. So how the brain changes with learning and how the brain may differ from typical development in individuals with disorders of reading or language. James has had over $9 million in extramural funding, has nearly 80 publications, and many published proceedings, invited lectures, and conference presentations. And this morning, James is going to talk to us about how the brain learns to read. So James, welcome to the Berkeley Center.
Really nice introduction. Thank you all for coming out so early, right after break, to attend this lecture. I want to extend special thanks to the Department of Special Education and Communication Disorders for hosting my visit. So, as Sherry indicated, my interests are quite broad, and I thought that for today I would focus on one aspect of my research, and that is reading. I will not be talking about our work on math or executive function today. So, again, thank you for having me. Before I start talking about reading, I'd like to first make some acknowledgments and give some thanks. The first acknowledgement is the funding that I've been fortunate to receive over the years. Most of my funding has come from NICHD, although I've had funding from NIDCD and also NIMH. I'd also like to thank the lab for their commitment to the research that we've been doing over the years. And I'd also like to thank the families who've participated in our MRI studies. You see a picture of 3 kids here. Those are professional actors. They're not real participants. They're actually a trio of children of a faculty member in our department. So, but we have kids just like this participating in our studies. So I'd also like to thank many of the students that have participated in research over the years. Here you see postdoctoral and graduate students. I'll be highlighting the work of some of these folks in the talk. I've also had the pleasure of mentoring undergraduate students over the years. I've actually directed 18 honor students while at Northwestern. Okay, so a road map. You can see Chicago, Lincoln. So I'd first like to consider why studying reading is important. And then talk about the interactive specialization model of brain development, which is very important for our conceptualization of reading. And then the bulk of the talk will be discussing neural changes associated with reading, and then neural mechanisms of reading disabilities, and then I'll end up with issues regarding early identification and instructional methods. So why study reading? So the importance of reading has been noted for many centuries. This is one of my favorite quotes from Abraham Lincoln. Writing is the great invention of the world, very great in enabling us to converse with the dead, the absent, the unborn, at all distances of time and space, and greatest help to all other inventions. More recently, Dr. Seuss has written, the more you read, the more things you'll know, the more that you learn, the more places you will go. So reading is fundamental to our society. Despite this, we all know that many children and adults struggle with reading. The U.S. Department of Education has categorized different levels of reading from advanced to below basic, and have suggested that about 20 to 30% of children in the 4th and 8th grades are below basic on reading. Now, those figures don't really talk about disability. They talk more about what we expect our children to be able to do in school. This is an interesting study that looks at the kind of the prevalence and the severity of learning disabilities in the context of many other developmental disorders. So here's an indication of the prevalence, here's an indication of the severity. I just highlight here the figures for dyslexia or reading disability, and you can see that the prevalence is moderate compared to other neurodevelopmental disorders. Severity is also moderate, so comparable, for example, to ADHD in prevalence and severity. Now, if we turn to number of publications and funding, we can also categorize this per million or per year, and you can see here the funding per million for dyslexia is quite modest. The publications are also quite modest as compared to other neurodevelopmental disorders such as ADHD. So I think there's a lot of work that still needs to be done in the area of learning disabilities. And in fact, if we kind of understand the nature and how to intervene, and we can improve achievement in our children, it could have wide-ranging effects. Here's just one recent study that came out of Europe, and they suggested that if we increase student performance by a quarter of a standard deviation over the next 20 years, they argue that the gross domestic product of the world would be 115 trillion times, 150 trillion higher, and that would amount to 40 trillion alone in the U.S. Of course, these are very difficult numbers to come up with, and people debate their accuracy, but I think we can safely say that it's a laudable goal to try to improve student achievement. So why study reading? The skill is fundamental to human society. Disability in this area is prevalent, and the cost of illiteracy is enormous. Okay, the next topic I'd like to consider is the interactive specialization model of brain development. We use this model to think about our work on reading acquisition. So I'm going to outline briefly this model. Some of you may not be familiar with it. It's work by Mark Johnson. So his central argument is that with development there's representational change, and this is reflected in specialization. So if you look at brain images, this may be associated with increased focal activation in the brain. And the argument is that this kind of increased specialization results in different pathways that are good at doing different things. So dissociable pathways with different computational trade-offs. What's really important, I think, about this model is this idea of this interaction between these different pathways or these different areas specialized for doing different things. So, in fact, if you read his work closely, what he argues is that it's the interaction between brain regions that drives development. So that drives the specialization of the cortex. We don't have any direct data to test this idea, and there's very little data to do that. But we're looking forward to testing some of these ideas with our longitudinal data, which we are collecting, but I won't talk about today. So this is a model that we'll use to conceptualize our work, and before I do that, I'd like to kind of very generally think about how this model may relate to underlying cellular events. So all of you probably know that there are these waves, these overlapping waves of synaptogenesis and later pruning. They happen at different parts, they happen at different times in different parts of the cortex. Simultaneously, you have this gradual increase in myelination, so this is white matter tracts, presumably reflecting enhanced connectivity. And then, of course, even when you're adults, you have experience-dependent synaptic plasticity, so you can continue to learn into your old age. So the idea is that there are large-scale changes in the kind of nature and pattern of connections. So perhaps the strengthening of connections indicates this interactive process between brain regions, and the pruning or the weakening of connections is the underlying cellular event corresponding to specialization. So is there kind of evidence to suggest that interactive specialization is a reasonable way to think about brain development? I'll just introduce this idea in the context of this study that looked at developmental differences in connectivity during the resting state. So essentially what they did is they looked at cross correlations between different brain regions and looked to see whether those changed over development. And what you see here on the bottom is an indication of strengthening of long range connections. You can see these blue lines. A lot of them are from frontal and temporal parietal regions. Those connections increased in their strength. On the top, you can see the weakening of short range connections, so indicated in red there. And you can see that those weakening connections were mainly in proximal locations, so within the frontal lobe, within the parietal lobe, within the temporal lobe. So the idea is that you have evidence both for an interactive process and a specialization process. So we wanted to look at this in a bit more detail. The previous study used global measures. We wanted to look at kind of hierarchical organization in the brain, and we also wanted to do it in the context of a reading task. The previous study was looking at the resting state. So, so we had a reading task. It was actually a rhyming task, and what you can see here is the network involved when you compare the words to some baseline. And in the red, you see all the kind of nodes involved in reading. You can do the reverse actually and compare fixation to the words, and you get a different network. But what we did was we used, I should say Jane, used some sorting and box cutting algorithms to kind of categorize the cortex at different levels or multiple scales. So of course we have the task network, we have the non-task network corresponding to these two contrasts. But through the algorithms, we also developed kind of an intermediate level of the hierarchy. We refer to that as blocks. And then we used actually the anatomy to come up with these regions. So we go from regions to blocks to networks. different scales. And then we look to see whether the patterns of connectivity varied as a function of skill. So you can take one connection, which you see here, and you can see how that's related to skills. On the top, you see an indication of a positive relationship with skill. On the bottom, in the blue, you see an indication of a negative relationship with skill. And you can actually look at that relationship across, every single connection. And roughly what you see here is in red, these are kind of stronger connections with increasing skill. Those tend to be off diagonal, so those are longer range. The ones on the diagonal tend to be shorter range, and those are more cooler colors. So those tend to be more negatively related with skill. So it's a bit hard to see the patterns here, so we can actually look at that in more detail at our multiple scales. So again, you have regional, you have interregional, you have interblock, you can even have cross-network. And we wanted to see how those different levels were related to skill. So what you see plotted here is actually the strength of the connection and whether it's associated with skill. So a positive number would indicate as you're getting higher skill, the connectivity increases. And what you see here is that the long range connection, so interblock and cross, increases a function of skill. The shorter range connections, the regional and interregional, are more weakly associated with skill. So we're going to kind of zoom in a little bit here on regional and interregional. We're going to do so by focusing on our different blocks as determined by this sorting algorithm. So it turns out that two of the blocks that we discovered essentially correspond to the core nodes of the reading network. And I'll get to this in a little bit, what those core nodes may be involved in, but things like inferior frontal, superior temporal cortex, inferior parietal cortex, those nodes are represented disproportionately here in blocks 3 and 4. And if you look at these kind of different connections in the different blocks highlighted in gray there, you can see that the short-range connections, the regional and interregional, are associated with skills. So as you get higher accuracy, you have stronger short-range connections. But if you look at the other areas, which aren't kind of typically associated with the kind of core reading network, it is in those blocks that you see this reduction of short-range connections, possibly representing some kind of specialization process. Okay, so to conclude this part of the lecture, I think what I've shown to you is this kind of idea that there are developmental and skill-related increases in interactivity, but also in specialization. And the last point was that appears to depend on the centrality of the regions to the task. So I'm going to focus here on the neural changes in reading acquisition. Remember, our connectivity study suggests that there were core nodes of the network involved in reading, and I'd like to step through what those core nodes are in our view. So fusiform, of course, on the ventral temporal cortex is very important in orthographic processing or representing spelling patterns. The superior temporal gyrus, the inferior parietal cortex, or the IPL, we argue is important, not just we, a lot of people argue is important in mapping between orthography and phonology. These 3 posterior nodes are all interconnected. And then the inferior frontal gyrus is involved in kind of accessing and manipulating these posterior representational systems. So this is kind of our working model of reading. It's very simplified, but I think it gives us some framework to think about how reading changes in the brain. So we're going to focus actually mainly on the fusiform cortex and the superior temporal gyrus. So I'm going to just talk about some of our studies as it relates to those 2 nodes of the network, so orthography and phonology. So much of our work has actually been cross-linguistic, and I'm going to talk about some developmental effects in English in the context of these studies, but I'm not going to really talk about the cross-linguistic differences. Just note that they're the changes that you see in Chinese-speaking children are different than English-speaking children. So the first point I'd like to make is that there are developmental increases in activation in fusiform cortex. And you can see that here. You can also see that here in this figure with the children showing less activation than adults in the fusiform cortex. You end up not getting that in the Chinese individuals. But at least for English, what we've argued is that this is associated with kind of the increasing elaboration of orthographic representation. So as you have more orthographic entries and the connections between those orthographic entries become more extensive, that demands more neural resources. We're also very interested in whether this fusiform cortex is influenced by phonology. So does your knowledge about sound patterns actually influence how orthography is represented in the brain, and is this skill dependent? So the way that we've tried to answer this question is to compare words with conflicting and non-conflicting information. So words like cake and lake versus words like jazz and has. So the argument, the basic argument is that if phonology has an influence on orthographic processing, the pattern that you see in the no conflict should be quite similar, or should be increasingly similar to the pattern that you see in the I switch those around. Okay, right. Switch them around. Yeah. The pattern that you see in the conflict should be similar to the pattern that you see in the no conflict, because kind of phonology influences the orthographic activation. So we looked at this as a kind of a function of the ventral fusiform pathway. And it turns out, people have talked about the posterior, the VWFA proper, so the visual word form area, and more anterior regions. So people have argued that this is kind of a critical area for processing visual word forms. So we looked at those 3 areas, and we also compared AV, or audio-visual presentations, to visual presentations. So the argument is that if you get kind of an effect for the audio-visual and not for the visual presentations, that would be reflective of kind of multisensory integration. So what we found was that if you look at the relationship between skill and this kind of conflict effect, you see that as you get higher and higher skill, you show greater and greater pattern similarity between the conflicting and the non-conflicting items, but you only do it for the AV, so the audio-visual, and you only do it for the VWFA proper. So to this, to us, this suggests that the VWFA actually becomes more and more multisensory as kids get higher and higher skill. Okay. So why does it do that? Well, presumably it's interconnected with phonological processing regions, and we in fact have evidence to suggest that the fusiform cortex is increasingly interconnected with phonological regions over development. So here we've shown this is a measure of connectivity between the fusiform and the superior temporal as a function of age. What we see is a developmental increase in the connectivity between those two regions. We only see it for the conflicting and not for the non-conflicting. This makes perfect sense. This is a rhyming task. It requires access of phonological representations. So the fact that you get it for the conflicting, which is more demanding, makes good sense. So fusiform seems to be multisensory because of its connection with phonology. We also wanted to see whether the phonological system was influenced by orthography. So we did this in the context of a cross-linguistic study, and we compared English to Chinese speakers. And what we found was that in an area of the superior temporal gyrus, there was an increase in English-speaking kids. And this increase was larger than the change that you saw in the Chinese-speaking kids. So here you can see it perhaps more clearly. This is the Chinese showing no real difference. Here's the developmental difference in the English. That's significant. That's for the conflicting. Here's for the non-conflicting. Again, no real difference for the Chinese, but for the English, you can see a difference. Turns out that the difference was even larger for the conflicting, suggesting that this is just an auditory task. You're listening to words, having to make a rhyming judgment. There's no reason that orthography should matter, but in fact it does, suggesting that orthography restructures the auditory cortex. We have additional evidence to suggest that restructuring hypothesis, because if you look at the correlation within the children between reading skill and amount of activation in the STG, what you find is a kind of robust correlation for the English children. For the Chinese children, you don't show any correlation. We have some ideas about why this may be the case in terms of cross-language differences, but for our purposes here, the important point is that an alphabetic system with relatively systematic mappings between orthography and phonology restructures the auditory cortex when you're doing a task that only requires manipulation of phonological forms.
Are these Chinese children in China?
Yes, they are.
I see.
So the last point I'd like to make in this section is that can we also demonstrate these kind of multisensory effects in superior temporal gyrus? So remember in the previous study we compared cross-modal, so AV conditions to unimodal. So on the previous study we just had VV, here we have AA. So we compared cross-modal to unimodal to get a sense of whether there was multisensory integration. We also have the congruency effect here. So remember, that's the difference between the conflicting and the non-conflicting. So if you show that some skill measure is related to the congruency effect in the cross-modal condition, then you have an indication here of multisensory processing being related to skill. So we looked at 3 different areas in the superior temporal cortex. One is primary auditory area, so Heschel's gyrus. The other is actually superior temporal gyrus proper. And the third was slightly more inferior, so the superior temporal sulcus. And what we showed is that in this area here, the superior temporal gyrus, you see that skill is associated with the congruency effect for the cross-modal condition, suggesting that as you get higher and higher scale, the superior temporal gyrus becomes more multisensory. Okay, so to sum up this part of the talk, I think we've established a developmental increase in the elaboration of orthographic and phonological representations. But importantly, these representations appear to become more multisensory through interaction with other regions in the brain. So next I'd like to consider whether we can demonstrate some kind of alterations in this interactive specialization process in reading disabilities. So this is actually my first study on reading disability, brain imaging and reading disability, where we essentially replicated what had been shown before. And if you look at all the core nodes of the network, it turns out that kids with reading disabilities tend to less robustly activate that network. And that's what you see here. You see less activation for the reading disability as compared to the controls. We're going to focus primarily on one region here, the fusiform cortex. And here we establish a difference. And we did so for the conflicting trials, the trials that are more demanding on orthographic and phonological processing. We didn't show a difference actually on the non-conflicting trials. So we were interested in whether we could kind of demonstrate a reduced influence of phonology on the fusiform cortex in those with reading disability. As you know, English is inconsistent, so I take it that you already know of tough and bow and cough and dough. Others may stumble, not you, on hiccup and thorough and slough and through. Well done. And now you wish perhaps to learn these familiar traps. A dreadful language may alive. I learned to speak it when I was 5, and yet to write it the more I sigh. I'll not learn till the day I die. So you know that English has a lot of orthographic to phonological inconsistencies, and that's indicated here. So you can have the same spelling pronounced in multiple ways. Turns out you also can have the reverse, so you can have the same sound spelled in multiple ways. So we wanted to see whether the fusiform cortex was responsive to this inconsistency in controls, and whether that was different than that seen in reading disabilities. So it turns out that if you look at typical kids, they show greater activation for inconsistent items. It's just harder for them to do. That suggests that the fusiform cortex is kind of responsive to this phonological manipulation. And it turns out that those with reading disability don't show that sensitivity. So they don't have a systematic relationship between consistency and amount of activation in the fusiform cortex, suggesting less phonological influence on the fusiform cortex in dyslexia. Again, that's probably due to kind of alterations in the connectivity of the fusiform with other regions of the network. This is a study that showed that the fusiform cortex was less robustly connected to other important nodes of the network. Here we have the inferior frontal gyrus and IPL. We weren't the first to demonstrate this, although we did extend what had been shown previously by showing, again, that this alteration in the connectivity was only apparent for these more difficult conflicting trials. The final bit I'd like to consider in terms of dyslexia is whether the fusiform cortex is even active when you listen to speech. It turns out that if I ask you to determine whether jazz and has rhymes, it turns out that you activate your fusiform cortex. You actually activate your orthographic system, and kids do it too. It turns out that those with reading disabilities do it less robustly. So this is an indication here of the fact that typically developing kids, when you ask them just to listen to words and make a rhyming judgment, they reliably activate the fusiform cortex, but kids with reading disability don't. So again, this is another, I think, piece in the puzzle suggesting that kids with reading disability have an altered fusiform cortex. The orthographic representations are maybe imprecise, underdeveloped, and perhaps one central reason that is the case is because there is this less interactivity with superior temporal gyres. I didn't show you any direct evidence to suggest that that's the case, and that's what we want to test in the future, right? We want to see early on whether it's kind of activation within a representational system or the nature of connectivity across the network that predicts subsequent changes in the brain. So children with dyslexia have deficient orthographic representations, and I'd like to argue that this is due to reduced connectivity with phonology. Well, again, I don't really have direct evidence suggesting that. Okay, so the final bit I'd like to talk about is implications for early identification and instructional methods. So a central goal of cognitive neuroscience of reading, I think, should be in determining whether we can predict future gains in reading. So we have one study which kind of is a first step toward this goal, and we took kids of different ages and we scanned their brains at time 1 and then at time 2, which was 3 to 6 years later. We tried to kind of predict how their behavioral performance on reading measures changed from brain activation at time 1. And it turns out that you can predict some of those changes. And it appears as though the fusiform gyrus is an important area that allows you to predict those changes. And I've circled it. I've circled the fusiform gyrus here. It turns out that there was a different relationship. So depending on age, so if you take older kids, there was a strong relationship. So so the amount of signal in the fusiform predicted how much they changed, so their reading gains. It turns out that less activation in the fusiform was associated with greater reading gains. Turned out with the younger kids, there was not really a reliable association. This kind of makes sense because people have argued that kind of the refinement of your orthographic representations is a relatively slow process that happens perhaps later in reading acquisition. Now this is just with typically developing kids of different ages. Can we predict reading gains in those with dyslexia? Here's a study which separated out kids with reading disability into those that showed a gain, those that kind of didn't show a gain. They also had some controls. And then they tried to kind of predict who was going to show gains, who was not going to show gains. They used fMRI, they used diffuse intention imaging, the combination of both of those. some behavioral measures. You can see all of those didn't have fantastic sensitivity and specificity, kind of below 80%. They also used kind of a technique similar to our technique looking at pattern similarity. When they used that technique, they were able to kind of accurately classify 90% and above. So those who showed gains and those who didn't show gains. And I've circled it there. Turns out that this, the area that was most predictive is right inferior frontal gyrus, not a kind of core node of the reading network. I'm not sure exactly what this means, but still it is encouraging that we can use, we could potentially use imaging to predict who's going to show gains and who's not. In fact, what we want to do is predict who's going to respond to intervention, right? And there's encouraging results in this regard. So this is some work using MEG, not fMRI. They looked at an early response using MEG at about 175 milliseconds post-stimulus onset in the left hemisphere. This is essentially your fusiform. And what they showed is that there was an association between this fusiform response and word reading efficiency difference score. So this is reading gain. And here you have the non-responders and the responders plotted separately. So, perhaps neuroimaging could be used to predict response to intervention. Of course, what you want to do is you want to predict, which individual will respond to which intervention. So to do that, I think we need to perhaps have some more systematic studies looking at the effect of different intervention approaches on the brain. And in fact, there's controversy even at a behavioral level, how we should teach reading. Of course, there's the National Reading Panel, which convened about 10 years ago now, and they stressed the need for evidence-based practice. They formed the What Works Clearinghouse at the Department of Education, kind of a compilation of what works in terms of reading interventions. I know there's some controversy around that, but I just went and tallied what works according to this website. And at this point, 2012, less than 50% of the reading programs that they reviewed had positive or potentially positive effects for reading fluency and comprehension. So there is some work to do, and we've have made some modest steps, and our steps are to kind of try to break down the reading process and look at relatively kind of specific effects of different interventions. So we've done so in the context of training kids in artificial orthography, so they learn kind of the pronunciation of kind of squiggles like that, and we do two different interventions. And one is a letter training, so you think of this as more phonics based. Another is the kind of word training, so kind of just training the pronunciation of whole words. And we look at what their gains look like over time, so their improvement in accuracy. In this particular study, we showed that offline gains, so this is gains between sessions, gains between subsequent days, was enhanced when you trained letters. It turns out that online gains are within a session, so actually learning when they're in the lab was greater for the whole word training. So there are distinct benefits here. Perhaps more importantly, what we showed was that the reading skill was kind of associated with these gains in a relatively specific way. So if you look at a standardized reading score, Here we have this reading score. The higher you are on the reading, the more you benefit in terms of offline gains during the letter training. If you look at the word, it turns out here the reading standard score is associated with, well, as you get better at the score, you show greater within session gains just for the word conditions. So there are these selective associations between skill and benefit of a kind of certain underlying process, say the offline versus the within session, that depends upon the intervention approach. I guess the main point that I wanted to make from those studies was that it's really important to consider individual differences in skill and how they modulate the benefit that people see from the intervention. So those who are higher skill or lower skill benefit from different kinds of intervention. And if we can understand that and how it's represented in the brain, then perhaps we could combine interventions, behavioral interventions with neurophysiological interventions. So some of you may have heard of transcranial direct stimulation. This is a technique that essentially is providing a low-level stimulation to the brain through an electrical current. It's on the order of, has anybody ever put like a 9-volt battery on their tongue? Go ahead, raise your hand. That's 9 volts. This stimulation is 1 to 2 volts. So it's very kind of low level stimulation. But there have been a variety of studies looking at the effect of this stimulation on both learning and performance, artificial grammar learning, verb fluency, word learning, and they've shown positive effects. There haven't been really many studies looking at the effect of the stimulation in reading. Here's a study with adults looking at the effect of stimulation of the left temporal parietal cortex as compared to a sham. So that's the real versus the sham here. Here's standard scores on some word efficiency, non-word efficiency, word accuracy, and non-word accuracy. What they showed was that this stimulation enhanced, word reading efficiency in these adults. And in fact, if you separate these folks out into below average versus above average, it turns out that the below average readers benefited most from this stimulation. So, so we're thinking about, starting some of these studies to look at how stimulation influences reading performance in adults. Obviously, there are ethical considerations involved in adults, but particularly so in kids, although some studies are being done in kids now. So I think that neuroimaging is useful in predicting gains in reading and in response to intervention. Instructional methods appear to have distinct advantages that are moderated by initial development and skill. And if we understand how this is represented in the brain, perhaps we could pair stimulation with intervention approaches. So the take-home message, I think our work supports the interactive specialization model of brain development and suggests that reading disability is characterized by alterations of this process. Neuroimaging has potential for early identification and intervention, and understanding learning disabilities is crucial for the success of our society. So I've highlighted, you've seen these guys all the way along. I've highlighted the work of different folks in the lab. Some have moved on, so Tali Baton, DJ Bolger, Fan Chow, and Amy DeRoche have all moved on to bigger and better things. And currently in the lab, we have Christine Brennan, Ruby Hammer, Chris McNorgan, and Jane Lang. So, thank you.
We have some time for questions.
Oh.
Hi, wonderful talk, thank you very much. I was curious if you had any sort of comment on the possibility of dynamically tracking learning and these reading skills acquisitions, maybe through some of these functional connectivity measurements, if it's possible to actually, in a much more small range, to be able to track what some of these interventions are actually doing and how they're building certain connections.
Yeah, I mean, we haven't done any of that work. I mean, most of the studies, the longitudinal studies that have been done are kind of pre and post. So, you know, before some intervention, after some intervention, or in the case of just typical development 1 year later, 2 years later, 3 years later on up. There have been some studies looking at you know, learning in adults, so at the learning process. So, for example, Russell Poldrack has done some studies looking at learning, and you know, has found that, you know, early in learning there's a greater involvement of the hippocampus involved in like instance-based learning, and then as you become more and more expert, there's kind of greater involvement of the caudate nucleus. So you can certainly image online changes in the involvement of different brain structures, say over the course of an hour. I don't know if that. But in terms of reading and reading disability, I know of no studies that have actually done that. Certainly not in kids.
So there was a slide where you looked at the cortical source of reading aids in children with dyslexia, and you found that it was in the right hemisphere in the inferior source, or it was unexpected where you found it. Do you think that that was some sort of plasticity or compensatory neural response in these children who had poor reading abilities?
Yeah. Yeah, that's a very good question. I mean, one of the general trends that people have argued in terms of reading is that there's a, you know, increasing left lateralization. So there's a shift from the right hemisphere to the left hemisphere. People have also argued that in terms of reading disability, you tend to get more right hemisphere involvement. Some people have interpreted that as a compensatory mechanism. The area of the inferior frontal gyrus that they reported is kind of more of a ventral area, and there are a lot of studies suggesting that that may be a very important area involved in response inhibition. So yeah, I'm not quite sure, but people have thought about it as, you know, in terms of compensatory, and it opens up the real possibility that, okay, well, you know, if we show that kids with dyslexia, we can't kind of change their prototypical reading network. We may want to, we can't normalize their prototypical reading network. We may want to take advantage of alternate pathways that they're using and strengthening those. But I think first we need to understand what those alternate pathways are, and just descriptively, and what they're involved in.
One other question. Regarding the developmental change, I noticed on one of the graphs the age range was 100 months to 200 months. Was that the typical age range you tested, or what were some other
Yeah, so all of my studies, actually most of the studies out there are roughly between, say, 8 and 13 years old. There are some studies looking at younger kids. That's our focus in the future, is to study 4 to 7-year-olds. So we're very interested in kind of earlier development. I mean, if you look at recently, we just kind of surveyed all of the literature, and most of the studies are on older kids. Some have included younger kids, but they've done a comparison across a wide age range. So, in terms of fMRI and neuroimaging, we know very little how the brain changes from 4 to 7. And one of the focuses of my work going forward is to look at that age range, but with particular interest in language impairment. It turns out that there's very little work on the neural basis of language impairment in kids, and it's really different actually from the work in dyslexia. I mean, dyslexia, there are, I don't know how many neuroimaging studies, but there are dozens. There's about a handful of studies looking at the neural correlates with fMRI, neural correlates of language impairment in kids, and really there are no studies that have focused on this kind of preschool to school transition.
James, I'm curious about, you mentioned about the individual differences having to be taken into account. So with neuroimaging, are there any key markers where when you're trying to make these predictions about someone's gains 3 to 6 years down the road, or someone's response to intervention, are there any key things you would see in your neuroimaging studies that would identify one as an individual difference? Or do those neuroimaging data need to be combined with other forms of behavioral or other kinds of data to really tease out these individuals?
Yeah, well, we're just, at the beginning, I think. I don't think we can make any, defensible argument in terms of can we use, data on neuroimaging data on individuals to inform us about what to do in terms of intervention. I mean, one comment, earlier was that, what if there's a lot of brain hemisphere involvement? Do we want to decrease that, or do we want to enhance it? I don't know. It turns out that in reading disability, I mean, my take on the literature is that the most consistent, reliable difference, the biggest difference between those with reading disability and not, is a change in the inferior parietal lobule. And remember that, I emphasize that the inferior parietal lobule seems to be involved in this mapping between orthography and phonology. So, if we see big individual differences on that, is there some threshold, that they'd have to be? Okay, well, if you're at, say, level of 10 on the inferior parietal lobule, I know that I can teach you the alphabetic principle, and you're going to behave like a typical reader in terms of the network that's activated. But if you're below 10, I should give up and try to do something else.
I just had a question, a couple of questions. One was related to how the students with dyslexia have been identified for your studies, and then you mentioned something about severity, of disabilities earlier. I'm wondering if imaging, if you found or looked at whether or not imaging can tell us anything about severity of the disability.
So in terms of the definition, we're not very sophisticated, I suppose. Generally what we do is we use single word decoding. So we have 4 measures: reading, word reading accuracy and speed, non-word reading accuracy and speed. So usually for kind of like the average of those 4 measures, we like them to be below like a scaled score of 95. But on one of those measures, we like them to be below a scaled score of 85. So at least on one measure, they're scoring in a lower kind of 15th percentile. In terms of individual differences within, say, those with reading disability, we're very interested in that because there is variability in that group, just like there is variability in the typical kids, and it relates to, can use that variability to predict who's going to respond to what kind of intervention or whether they show compensatory processes. You remember I showed you the data, just give you one example about how this individual variability seems to be important. Remember I showed you the data of the consistency effect? So yacht, doesn't make any sense how we spell it, right? Typical kids show greater activation for inconsistent compared to consistent. It makes perfect sense. I mean, you kind of have to work harder for those inconsistent items. If you look at, and that's as you kind of increase in skill. Turns out that in kids with reading disability, they show exactly the opposite. So in fact, the kids with reading disability show more, as they get higher skill on a phonological measure, they show greater activation for the consistent and less activation for the inconsistent. What does that mean? Well, what it means to me is that what we do with reading disability is we train these guys up on phonological awareness, and they become expert at that, and they can decode regular items, and they robustly activate their network for words like lake, cake, make, fake. They follow the rules, right? And you give them an inconsistent word, and their system breaks down. They can't deal with it because we focused a lot on the phonological awareness. So, so individual differences in the reading disability group are very important, and we need to better understand that. I mean, it relates to the subtype issue, right? I mean, somehow that has been de-emphasized, particularly in the neuroimaging literature. But kids have strengths and weaknesses. So one dichotomy that has been used in the field is the surface dyslexics versus the phonological dyslexics. Surface having more orthographic problems and phonological having more phonological problems. So we need to understand the heterogeneity of that group and how it is reflected in the brain. I agree with you.
In the interest of time, and there is a class that needs to
Yes,
get in this
sorry.
room, I just want to say thanks to James one more time. Let's